Hello, everyone. My name is Anastasia. You probably know me from C++ community in St. Petersburg. And our speaker today is Titus Winters. Titus is a senior staff software engineer at Google, and he has worked there since 2010. And he founded AppSail, Google's open source C++ library, which you definitely have heard about. He's also for arbiters for Google's official C++ style guidelines and the lead author for the book Software Engineering in Google. And I highly recommend you reading this book, which is the collection of Google's best practices, which can be applied to others, even if you're not as big as Google. And of course, you might have heard about Titus' proposal paper on C++ ABI called Now and Never, which triggered a valuable discussion in the community and hopefully encouraged everyone in the C++ community to think about this important commitment. Today, Titus will talk about the design for systems and interfaces that will be in use for a long time. Some aspects of this talk you might have met in his book, Software Engineering Google, but today you can learn a lot more. So Titus, hello, and how are you today?
I'm great, and I'm very flattered. That was a very, very flattering introduction.
Thank you very much. I want to remind to all our listeners that you can ask questions in the player you're watching us right now or in the dedicated Telegram chat. And you are also encouraged to rate the talk. And after the talk, you're all welcome to the discussion. So Pavel will be helping there with the discussion instead of me today. So, okay, Titus, before we start, I actually have a quick question to you before. So CPPCon this year was a hybrid, and you were there in person. So how was it after a long break from in-person conferences?
It felt really, really nice to have some little bit of back to normal. It was great to see some people in the community. It was great to see some of my coworkers from other offices, from other cities. I was only on site for a couple days. I had personal commitments back home, but it was very pleasant. It was certainly smaller. It was different. I think they said there were only 200 or 300 people on site, which is significantly down from the highs in 2019, for instance. But it still had that sort of feeling. It was like getting back to normal. And I think CPPCon I've been to more than any other conference, so it's kind of like touching home base. So it felt real good.
Yeah, great. I was there only online. I'm really looking forward to being back to in-person events. But you know what? I will be really missing these kitchen photos in offline. Okay. So I think we can start with the talk now and learn about the design. So let's go.
All righty. So if you listen to colleagues of mine, like Chandler Carruth, people that work in optimization and think so deeply about why C++ succeeds as a performance-oriented language, you will hear phrases like higher level of abstraction, coupled with the normal C++ slogan of our abstractions are zero cost. When we have more expressive tools to express our intent, and the compiler can see that we haven't pierced those abstractions, so for instance, it can do the escape analysis proofs, it can more effectively reason and optimize. When we have higher level abstractions and use them consistently, these are things like even just vector instead of a pointer and a length, we can tweak them in a centralized fashion in response to changing conditions. So for instance, if the ratio of RAM to CPU costs changed dramatically over time, we could imagine changing the constant that was used when we're, say, resizing a vector, just the normal growth patterns. If we discover that CPU costs are extra expensive, and we see that our hits to the allocator, copies and moves of elements in our vectors, these aggregate CPU costs are bad, then you could change vector from doubling in size natively to growing 3 times. Or on the flip side, if you're spending too much on RAM, you could grow by only 1.5x instead of wasting a little bit extra RAM during your resizing operations. You could resize more frequently, but keep the bounds closer. The abstraction vector helps the optimizer. The consistency helps maintainers refactoring, maintain the large code base. And this centralization acts as a choke point, as a useful lever for those that are trying to balance aggregate resource costs. For another perspective, if you listen to colleagues of mine like Hyrum Wright or Matt Koulakundis, you'll also hear stories about our attempts to optimize and improve interfaces through refactoring, improve efficiency through refactoring. A lot of our long-term work at Google requires us to have the ability to change code, sometimes centrally and sometimes diffusely across the whole code base. This is, again, an exercise in finding the right abstractions and then either changing their implementation so that all of the users get the boost at once, like tweaking or resizing parameters for vector, or upgrading to get better abstractions individually in dozens, hundreds, thousands of calls across the code base. We see this in most of the traditional thinking on refactoring and optimization. Right? I remember being told as a student that 80% of your cycles are spent in 10% of your code, that there's a hot path or a busy loop somewhere that's doing the bulk of the work for any particular computation. And that is unfortunately not particularly true in our experience today. The profiles tend to be a lot flatter than that across the entire code base, across Google's fleet, for instance. But there are still a few places that do use up a lot of juice, as it were. And whenever we can improve that, whenever we can reduce our resource costs, then that's a good thing. These sort of centralized operations are things like tweaking the memory allocator or changing allocation strategies for common vocabulary types. Optimize the network stack if you're using one like RPC system consistently. Find your concurrency abstractions, optimize mutex. Right? These are changing one thing centrally in a very traditional optimization fashion. But you also see that you can optimize broadly. Right? You find a pattern and you make that pattern of changes all over the place. This could be things like changing parameter types or removing redundant copies, those sort of things. And this can add up. Each individual change is not going to be a big deal. But if you do this consistently and you make it easier for people to copy and paste the right thing, you get to better results. But both approaches, either centralized or distributed, require some amount of consistency. You could optimize the allocator, but it's hampered if the old implementation was giving out tuning parameters and controls that get in the way of that optimization. We can build tools to remove copies or pass more efficient parameters, but if your team built a string type that we've never seen before, then our pattern matchers aren't going to kick in, and we can't optimize that. You're going to need consistent and understandable abstractions. And yet, a lot of the discussions in the past couple of years, or at least the ones that weren't pandemic related, seem to converge around one central theme. Extra extension points and configuration knobs are sort of getting in the way of these optimizations, especially in cases where the configuration abstraction itself is sort of piercing through and letting the details of our operations, of our interfaces leak. When we have the wrong knobs, when we have the wrong abstraction for configuration, then this gets in the way of both our centralized or distributed optimization work. Because critically, we have to recognize that configuration is an abstraction itself. It can be well designed or not. And just like any other sort of design, any other sort of abstraction, we lose the ability to reason about changes when we can't know how an interface is being used. If it's all runtime configured or configured by some network call, it's very hard to prove what the behavior is in the general case. And remarkably, configuration often seems, at least common forms of configuration, often seem to exist specifically to pierce through the abstraction, to tweak internal parameters that really we don't have any business as users touching. Think about this. When you have a system that works on exactly three types, say int and double and string, there's a certain level of reasoning available to you. You can look at any proposed operation on that system and do the math internally, like do the work in your head to see how that operates with int and double and string. When you have an I/O streaming gadget that has an internal buffer of 64 kilobytes, you have a certain amount of understanding of how that's going to interact with I/O operations and the memory allocator. But when you extend your system to arbitrary types or user configurable buffer sizes, it's a whole lot harder to prove that any change you make in the future is safe, and much less to prove that it's going to be a performance boost. And yet, none of us is surprised to see requests from users that enable these sorts of changes. They might say, hey, this buffer is too big on my platform. Could I get a knob to specify it directly? Or I've got my own string type. Can I use that instead? From a user satisfaction or maybe even product quality perspective, saying yes to those requests feels right. It's one user-provided buffer size. What's the worst that could happen? What we increasingly find is that these matters need to be handled with care, especially if the interfaces you are designing are going to be around for a long time. Like, what is the right size for an intermediate buffer in a streaming I/O interface? Right? Like, we could do an operation here to ask, like, how many of you think it's going to be okay at 256K or less or more? We need to tweak that. But whatever number we come up with is going to be one specific number, right? Imagine we agreed on average for most of the things that we're working on today, it takes 64 kilobytes for that to be a decent average choice. Now, how about if I told you that that same code is going to run on the 486 that I grew up with? Is that still the right size 30 years later? Or if this code is going to live for another 30 years? Of course not. You're going to need some ability to tweak it. But what I like to argue, among other things, is that giving users the direct ability to specify that buffer, especially dynamically at runtime, may not be the right answer. There are sometimes better ways to express these things. It might be the case that you want to infer the right value from the properties of the platform that you're building and deploying for. It might be the case that you want this to be entirely centrally controlled. It might be the case that you figure out, it's just a buffer size, I'm just going to pick a number and move on with life. And we can reevaluate as a one-off operation every 10 years. There are often higher levels of abstraction and ways to approach this. Everything interesting in software is a matter of trade-offs. And this is, I think, the fundamental trade-off at play here. For systems that are going to live for a while and that are going to be used by more than a few people, how do you configure them to allow them to be used in new environments and with new use cases without hampering our ability to make future changes and optimizations? In this talk, I want to specifically focus on three main forms of customization and extensibility. There's configuration settings, tuning parameters, optimization knobs. These are things like setting timeouts and buffer sizes. They tend to not impact the semantics of your interface, of your abstraction, of your program. They tend to often be more optimization and performance. There's feature flags and experimentation. I work for a web-focused company, and we've written quite a bit about the use of runtime configuration for safe rollouts, experimentation, and feature releases. And as it turns out, I think there's some overlap between the ideas and practices regarding feature flags and proper behavior configuration during a refactoring or migration. And then there's extension, letting users provide their own callbacks, algorithms, data structures, types. But before we get into that, it's worth pointing out a little bit of context. Right? I've been working on C++ library infrastructure at Google for more than 10 years. And in fact, I wrote up a brief summary of my philosophy on design and some of these very questions about 5 years ago. And I'm not going to say that my approach is the only correct answer, right? It's design. There are not a whole lot of deep fundamental truths that we agree on yet. Some of it is context dependent. Some of it's a matter of choice. Some of it's just fashion. I don't know if we're fully aware of those distinctions yet. But for what it's worth, my philosophy of design in my own words. I said all those years ago, people often seem surprised at my priority, right? Arguments of, hey, we could build X don't tend to interest me. Adding a feature that is used rarely is often worse than not building that feature at all, especially for fundamental low-level interfaces, for several reasons. If the vast majority of your users understand an interface's behavior through the lens of the default setting, the 1% of users that change that setting are at risk. APIs that are built at a higher level have a good chance of assuming the default behavior, and they leave your 1% semi-supported. And I regard that as usually worse than unsupported because it's going to fail late in development and in surprising ways, and it's just going to be hard to undo. There is, of course, Hyrum's law still applies. Mostly I have to mention this because the more surface you expose, the more that your users are going to constrain what changes you can make. Excuse me. And the compiler and the type system are very good places to have invariants. Correctness proven at compile time is preferable to discovering the same things at runtime. That is just good application of the whole shift left terminology. It's cheaper and more reliable to detect problems statically at compile time, so let's do that if we can. I think that also applies to configuration. So compile time configuration, or configuring based on target platform instead of dynamically at runtime, or just not configuring at all. But regardless, earlier and more statically tends to be much, much easier to reason about and maintain. These general design priorities and ideas have been pretty resilient over the years. So let's try to apply this to configuration. For the purpose of this talk, once again, I'm going to talk about this as specifying inputs and parameters to tweak the general operation, performance characteristics of the component. There's settings, knobs, timeouts, targets. We configure things all the time. Your faucet has one major mode, off and on, probably as a gradient, right? With a pretty important piece of configuration in it, hot and cold. But as anyone that has used a faucet can tell you, that configuration isn't perfect. Just because you turn on the faucet to full hot doesn't mean you always get hot water. You're configuring the steady state or the ideal state, or maybe you're just telling the faucet system which of its inputs to prioritize. You hope that you're specifying an output, but that specification is inexact and aspirational. Your thermostat does this same behavior, right? It's also off and on, but with a slightly different configuration. You pick the temperature you want, and it does what it can to make that happen. So I think that's maybe interesting. Two designs for things that we're mostly okay with that have very different implementations. Setting a target directly and having a computerized feedback loop and sampling system versus controlling the inputs in a way that leads to an expected target. But both configurations, I think, are focused on the outcome. Are there other tools and utilities and technologies in our lives and our environments that are the same? How about the humble microwave oven? For most of us, the only configuration here is how long do I cook this for, which is a slightly different form of configuration than the previous two. If you're very fancy with your microwave, you might also adjust the power settings if you're getting really gourmet. And if you're feeling extra lazy or extra lucky, there are these pre-programmed special function settings like the popcorn button. And this seems in line with something like a thermostat, right? Where you're picking the outcome that you want, and you leave the mechanism of how to achieve that to the programming. But here we start to see interesting problems. Most purveyors of popcorn, specifically say on the bag, don't use the popcorn setting. Like, I searched for public domain images of microwave popcorn, and the very first image that I found had exactly that warning on it. If you dig into the details at all, the popcorn setting isn't magic. It's just basically taking the average power level and timing across a variety of popcorns. It isn't paying any specific attention to the details of your popcorn. Some newer microwaves might try by adding a humidity sensor on the notion that popping corn releases a lot of moisture, so if the humidity level goes up and then starts dropping again, you probably have popped it all. But even still, popcorn manufacturers point at a better answer to identify when your tasty snack is done popping. You listen for the popping to stop. So on the one hand, the popcorn button, where you're picking an outcome, is a very tempting idea, but it sort of falls short because the implementation doesn't measure up. And that leads to an interesting question. Should I do it directly because I know better than the microwave? Or should I use the popcorn button because it expresses my intent even if the results are currently underwhelming? Maybe there could be a software update to my microwave that fixes all of this. In this case, I know for sure that my microwave isn't going to magically gain the ability to properly pop popcorn, so I'm going to do it directly and be sad about the realities of the world that make that button so misleading. But interestingly, part of the question here is there someone actually responsible that I trust that is going to help close the gap between the intent I expressed and the outcome that I got? I would argue pretty clearly that there isn't in the case of the popcorn setting. A commodity microwave oven just doesn't have the hardware, much less the software, to get the popcorn button right. So I know from the start it's never going to get any better, and I can just stay away from it. But hopefully, the things that you are configuring, especially software, aren't like that. I'm pretty sure that good quality for configurable interfaces is tied up in either everything is perfect and will stay that way for the vanishingly small number of things that don't need to change over time, or the system is malleable enough for us to give you better results in the future if you express your intent and trust us enough to change things to help get there. So from looking at just the design of things around us, my current reading on what works is we like to control outcomes, the thermostat, but we'll settle for controlling inputs when those match our intuition. That's using the faucet or the manual microwave controls. But mechanisms that purport to control outcomes and do a bad job of it and have no chance of being fixed in the future are kind of an attractive nuisance, like the popcorn setting. This is a computers and C++ conference, so maybe we should start looking at those things. What sorts of configuration do we commonly see in our C++ jobs? We'll start with something just related, the compiler. Compilers have dozens, probably hundreds of command line flags. But in my experience, we talk about two classes of flags more than anything else: optimization and warnings. What are we optimizing for, and what classes of warnings are we going to diagnose? You might already see where this is going. With optimization settings, we tend to express those in broad strokes, desired outcome fashion. Turn on aggressive optimizations versus optimize for binary size versus just build this as fast as you can. We don't get down in the fiddly parts, right? The flags are going to be things like -03, not -0, unroll loop count equals 5. Right? We say broadly -w all much more often than we list all of the individual warnings for w all. And we chuckle nervously at the fact that w all isn't usually actually all of the warnings. It's just the generally applicable and high quality ones. You can, in some cases, break open these abstractions and toggle the more fiddly bits, specifying specific optimizations to engage or disengage, specifying specific warnings to turn on or suppress. But we tend not to, and we probably shouldn't in general. -0 is kind of like the thermostat. You aren't telling it how long to run. You're just telling it what your goal is and letting it do the best job possible in achieving that goal. It kind of is going to pay attention to the details better than you are, and it knows more about how those interact than you do. And even if w all is misnamed, you're still broadly just saying, keep me on the straight and narrow, don't let me do anything too weird. Let's look at some more examples. Maybe also in tech, but in places where we think the design isn't satisfying. And rather than throwing shade at someone else, I'll use a slightly sanitized example, configuring a buffered reading interface that we use internally to read certain forms of sequential structured data. I used to maintain this interface for a number of years at Google. So here are the current configuration options for this reading interface. There's memory budget. That is ideally the memory budget for the internal data buffer. There's seek back. Since we're reading sequential structured data, if we decided to arbitrarily seek through the file, that wouldn't necessarily put us on a structure boundary. So we might skip backward by up to this amount to try to find the synchronization points within the stream. This is mostly useful when we have very large files like index files, and we want to parallelize those across a large batch of batch processing, parallel processing. There's this enable async IO Boolean, which says, are we trying to make read calls asynchronously, either by spinning up another thread or relying on non-blocking file operations? If enable async IO is set, then we have a few more settings. There's buffer size, which this is the actual memory budget for the internal data buffer, and the memory budget minus the buffer size becomes the budget allowed for other asynchronous operations. Otherwise, this flag is ignored. The look-ahead budget, how much prefetch to do while doing asynchronous I/O. This should be less than the buffer size. And prefetch on open, which is, do we prefill the buffers starting at construction, which amusingly, I think, doesn't actually have anything to do with enabling asynchronousness. It could apply otherwise, it just happens to not be configured that way. So this is all very clear and straightforward, right? To be fair, this example was drawn from an interface that has been our textbook study on things that evolved without much oversight for a few years. Pretty much any proposal that was backwards compatible and where the tests passed were accepted. And now we sort of know hands-on what happens when, hey, we could make this change is used as a proxy for, hey, we should make this change. In any case, if we compare this to the lessons that I think we've tentatively been extracting from my previous examples on configuration, there's a lot more math and control logic in here. Subtraction on byte counts, Boolean comparisons, distinct modes of operation for enable async IO. It's pretty fiddly and hard to connect. How do I configure these things to get the results that I want? But by comparison, I don't think any of this configuration is actually tied to those outcomes or intent. If we were looking at configuration based on intent, I think you could do a lot better. Maybe you would have just one enum and optimize for what do you care about most in the use of this interface? Total amount of CPU cost, the number of I/O operations that you're using, or memory budget as a whole. You might extend that if you wanted to be about as equally semantically robust as the previous version. You might have a maximum memory budget. You might have a hint as to the size of the records that are being written, since that is actually semantics for the seek back details. You might specify how many threads are we allowed to spin up to prefetch. And the question now becomes, who would prefer the old set of options versus this proposed configuration? Or would you prefer this proposed configuration if I told you that a very good engineer is going to handle the details of making the optimize mode do the right thing so that it's not just the popcorn button? And I think every time that I've done this talk live, I've gotten pretty solid consensus that this outcomes-based configuration is a heck of a lot easier to understand and work with. Now, let's make it a Titus talk and point out the idea that time is going to cause change. How do these two approaches to configuration function? How do they interact with our needs as the technology around us changes? So let's imagine that a maintainer of this library identifies new optimization opportunities. There's a new compression system out there. There's a change in file formats, whatever. Or there's a new understanding of the trade-off between CPU and memory costs. What of this configuration approach, strategies for configuration, which work better and which don't? With the outcomes-focused configuration, the only requirement here is that the maintainer is trying to honor those configuration requests. You could have default sizes for your buffers per mode, depending on CPU or memory or I/O operations. And as you learn more about the system in the wild, you can change those sizes and re-optimize. All that's really required from the API is the semantics of reading sequential records out of a file. So long as the set of records that it finds don't change, all of the rest of this is just performance and optimization. Of course, Hyrum's law does apply. Some fraction of users are going to depend on the particular set of calls to reading from the underlying file, but the ways that you can express such dependencies are pretty obviously clever and brittle and would take a lot of work. So you have to be interposing system calls and things like that. And I think it's relatively unlikely that most users are going to do anything weird like that. So I think with fewer interfaces exposed and higher level interfaces and more orthogonality in those, then it's a lot harder to constrain the implementation details based on Hyrum's law problems. As a result, you have more flexibility. When RAM prices spike, you could, for a modest amount of effort, or maybe even none, change your allocation sizes to match and see a benefit for all users of that interface. But with the more fiddly configuration, it's a whole lot less clear. Right? When you're specifying, buffer size, you're pretty clearly leaking the implementation details. Right? Just seeing the configuration options for memory budget, seek back, and enable asynchronous I/O, you can probably start sketching out in your head exactly how all of this works. We could re-implement that logic pretty easily. But that leaky abstraction also means that we're giving users more ways to think they understand all of the details, more control over things that should be internal, and thus more ways to sort of screw things up. Let's take memory budget, for example. Most of the time, people don't seem to care about this setting, and they just rely on the defaults. Out of 13,000 uses of this interface that I could find, only about 100 are explicitly configuring the memory budget value. Remember what I said about it being a red flag when your options are rarely used? One of those 100 sets the value to 256 bytes, which seems kind of horrible to me, right? You're going to pay the I/O costs of doing reads at less than a kilobyte granularity. That seems wild. On the other hand, one of those sets the buffer size to 256 megabytes and spins up one reader for each of n different files. And I think that n could be 100 or 1,000. This seems a little excessive to me as well. The rest in between there are mostly hard to interpret. I have no idea if they're actually better or worse than these outliers, which is also kind of a problem. I can't tell. So now imagine you're a maintainer of this library acting on information about relative resource costs, RAM and CPU. You've given users control over the size of that buffer. So here are the important questions. How many of those did that based on evidence or optimization versus how many of them just picked a number? Even if they did the research to set that value precisely and optimally at some point in the past, is it still optimal? How long does that research hold? How many of them are going to scream if you change the behavior on something that they have hyper-tuned? When you have only these fiddly sort of configuration knobs, you can't really tell what their intent was. Did they set it to 256 megabytes because they know that the files that they're reading are always about that size and they're optimizing for I/O operations? Did they set it to 256 meg because it runs during startup of a process that is going to have much, much larger RAM usage, and they know that that larger buffer is always available, and therefore they can reduce CPU cost? Is there any way to tell? In a perfect world, there would be a comment explaining the rationale for this setting, but that's not really going to happen in practice. Unlike other things that we know how to change safely because of tests, these sorts of configurations don't usually result in semantic differences, mostly just timing and resource consumption. And as far as I know, nobody really has a robust model for testing these things, right? Such tests, if they existed, are often flaky, and they certainly don't match the normal pass-fail semantics that we hope for from tests. Under the model, under the belief that change must be possible, these granular performance tuning operations kind of become a real stumbling block. And maybe that gets to the heart of all of this. In the same fashion that C++ wins when it provides higher level abstractions, it provides vector, it doesn't let you donate or steal the pointer that vector operates on. It's abstracted, it's sealed. We win in configuration when you provide higher level configuration knobs and fewer options. And this is important because every time that someone resorts to leaning on one of the smaller fiddly options, some fraction of them are wrong from the start. And more importantly, they become what we would call haunted graveyards right away. That is, when you come across someone setting the memory budget to 256 megabytes, it's really hard to evaluate whether that choice continues to be right. So I pretty much guarantee that anyone that spots this code in the wild is just going to leave it alone. Changing it is scary, both because change can sometimes be scary, and because there are so many possible options. And the reasoning, the intent for that original choice is completely hidden. It's now a haunted graveyard. It's a part of your system that everyone kind of knows is there, but they're afraid to touch because no one really understands what will happen when they do it. Similarly, we sometimes have systems internally with configurations for things like, how many threads should I use? Imagine we default it to 16 threads in some parallel processing system in the first version. But some users find that for their particular workloads, they get better throughput when they reduce that number of threads to 8. So they set it manually to 8. They override the behavior. Then we optimize things in the back end. We change context switch latencies. We improve I/O throughput, change the default number of threads to take advantage of those optimizations. But anyone that already hard-coded a value misses out on some fraction of those gains and increasingly has the wrong values because other things in the system around them have changed. It may well be the case that after this happened, those users would have been best served with 32 threads, or they wouldn't notice just going back to the default. But it's hard to prove that their settings are out of date. No tests are firing to suggest that something's wrong. And so they stick around and sort of pessimize all of this. And we see this so frequently. Does this mean that all fine-grained configuration knobs are bad? I don't think so. Right? Having control over singular specific details is sometimes necessary. Setting a timeout or providing a port number, a user name, a database path. These all seem like the right level of abstraction as far as I've seen. But those all have a semantic meaning from outside the abstraction, which is very different in my mind from the memory budget example. Interestingly and satisfyingly, since I started trying to frame my thoughts, since I started trying to make concrete all of these ideas on configuration, I found a few other people that have independently come up with roughly the same list. It's the sort of thing that's never going to be easy to prove, like I think a lot of design guidance, but it does seem broadly applicable. Our configuration needs to be orthogonal. It needs to be very focused on outcomes and intents, right? It needs to be minimal, and it needs to be easy to reason about. You should be focusing primarily on the outcome behavior, not the implementation details. Another important place where configuration and options come into play is during migration. I've given similar examples in the past, but it bears repeating. We also use configuration options during migrations, during refactorings, especially to express the intent of do what this API used to do. This is, I think, a textbook example of how we changed the defaults for an existing system. I gave an example in my 2019 CPPCon talk on design, where we changed Abseil's stircat when it was formatting floating point values. We did this before we shipped stircat. Originally, stircat was printing all of those doubles at full precision, and we found most users didn't actually want that, and we were spending a lot of CPU on it. So in order to reduce that down to a much more reasonable amount of formatting and a more reasonable amount of CPU cost, we find all of the places where we're passing a double to stircat and wrap them in a call to legacy precision, which initially does nothing. It just returns either the string or the double version of that input. And then once everything in the code base is using legacy precision instead of double directly, then in a single change, you can change the behavior of legacy precision and the default formatting. For any call where you can prove it didn't matter in the first place, you can either skip the change or clean it up afterwards. This same approach works for all sorts of things. In fact, one of the earliest large-scale changes at Google was done in exactly this way. We wanted to change the default visibility for our build rules within the code base, the interdependencies between libraries and packages. And step one in this is to make the current behavior explicit. The behavior had been that everything is public and people could depend on anything, even stuff that was marked internal for other teams. It was kind of not really enforced that it was private, that it was internal. And so from a functional perspective, from a semantics preserving perspective, you go through the code base and you add visibility equals legacy public to every build file. And then when every file has that in there, you flip the default. Any package that doesn't have that sort of visibility declaration now defaults to private from that point on. While you're in the middle of a migration, this is a very useful technique. But I think it's also important to note that it is about intent. In both of these examples, you're making code changes and behavioral changes that make the original behavior explicit. And thus you are matching the original intent of the user. It is still outcomes focused. We might look at why we call these things legacy. It's at best very, I'm a sign, not a cop. This is not strongly enforced, but it does give you a pretty strong signal for at least new users that you probably don't want to use this setting in new code. And I don't have a clear answer for when the naming legacy is the right answer, but it might roughly be this option is going to be here forever. And we want a spelling that says only, this is the old behavior, I don't know if it's right. That is, it encodes both the semantics of the old behavior and the fact that no human has evaluated whether this is the right choice. You could imagine someone as a background sort of cleanup task trying to go through and evaluate whether that was actually the right choice or just a legacy default behavior. Or you might say, call it legacy because the option is going to be there temporarily, and you're just warning people away from adding more use in the meantime. By comparison, naming such a toggle legacy is probably a bad idea if it's a behavior that you expect to support forever, and you don't think that today's usage of that behavior is wrong. And that sort of brings us back to this slide. At one point, I was trying to add extra bullets to account for this sort of configuration to support maintenance and refactoring. But in the end, it's really just about outcomes and intents, not implementation details. It's maybe leaky in that it shows what the default used to be, but that's not the same as what we usually mean when we say the abstraction is leaking. Where else do we see runtime configuration happening regularly? Since I work for a web-focused company, we'll think about production. Experimentation, release flags. This is another incredibly important domain for configuration. Both the SRE book and the Flamingo book talk about feature flags for configuration. This, in many respects, is part and parcel with general DevOps policies and trunk-based development. Don't rely on dev branches, commit to trunk. If your feature isn't ready to be deployed to users yet, don't call it. But you do include the tests for it. Your feature will be built into the binary for development builds. It might be stripped out in release builds, depending on how your system is set up. And when it's time to see whether the feature really works in the wild or is providing value at all, then you use some experiment framework or release algorithms to turn on the feature for some subset of usage, either as an A/B test or as a gradual rollout. If it turns out to be bad, you can cancel the A/B test early. If it If it turns out to be buggy, you can slow down the rollout or cancel the rollout. And you can, at runtime, do those things without penalty. This sort of behavior requires two major components. The functionality is gated by these feature flags and configuration. And the setting of that functionality is controlled, depending on how you're operating and how you ship your code, by either a release engineer enabling the feature, some experimental framework that's handling the A/B testing, or some rollout system that is rolling out new binaries and or configuration changes to those binaries. This is a really valuable mechanism to go alongside release rollout procedures. And I don't have a whole lot to say about that, except that as far as I can tell, the same principles from earlier apply. This works best for bigger bundles of functionality, not little fiddly controls. Right? You're going to add feature flags and rollouts and experiment flags for outcomes, for full features, for all of those things, not for just changing the internals, not for just tweaking the optimization of something. So we could add, configure your whole binary, especially in service of a good release engineering, to our list, but it's really the same as just being focused on outcomes and intents. It's that second bullet again. I will definitely say, remember to clean up after yourself at the point that your feature is fully rolled out. It's been stable for a while, then please, please, please clean up after yourself. Do what it takes to remove any old code paths that aren't reachable, make it obvious that your feature is enabled. And that's a thing that you just have to commit to, and it's hard because it's really easy to always put it off. But in the end, if you don't, you'll find yourself having tens or hundreds of dead code paths and long disabled features that don't actually interact with one another or even work anymore. Before we move on from configuration broadly, a couple points come out of all of this for me. The first is just how often we see these sorts of things. Even in the low-level guts of the language, we find some value in specifying these sorts of platform configuration and optimization properties. The stood hardware destructive and hardware constructive interference size constants were added in C++17 in an attempt to make some properties of the platform clear. If you're building from source and your compiler is well-tuned for your target platform, these can basically clue you in to the necessary spacing to keep things packed into one cache line or the spacing needed to avoid false sharing and cache contention. But these are wholly non-semantic. This is definitely configuration. Setting these wrong, ignoring them, or using them inappropriately isn't going to cause correctness issues in general, just slowdowns. And that means two things, right? You shouldn't be referencing these in tests or asserting anything about their value because it's not a matter of correctness. And more frighteningly to me, we don't have clear mechanisms for changing or for evaluating whether a change to such values is acceptable. Almost everything that's been written on testing, refactoring, maintenance assumes that you could use test failures as a prediction of whether a given change is safe, primarily by virtue of detecting unexpected behavioral changes. That seems to clearly not apply here. Even places like Google that are very good at general in testing and refactoring are still hunting for ways to make changes to these sorts of optimization configuration points safe. We don't have the machinery to predict the acceptability of a configuration resource optimization sort of change. And that's going to be an interesting place for us to be looking at our engineering practices for the next few years. What happens, briefly, when we step up the question of configuration by a level of abstraction? Instead of you handing me values to configure my behavior, you hand me functions or types or the like. You probably experience this most immediately with one of two things, either callbacks or polymorphism. There are some design lessons to be had here, but I think they're less deep of an insight than we saw with configuration, so I'll go through it pretty quick. With callbacks, I really just recommend define the callback or the context that you're going to invoke this callback from. Be very, very, very aware of Hyrum's law. Regardless of what you document, people are very quickly going to come to depend on which thread is your callback being called from? Which thread is it not being called from? Are there any locks being held? Hopefully not, but I can imagine that there are some scenarios where that's not true. In the case of event listeners, where more than one callback might be triggered for a given event, what order do those callbacks happen in? In the case of eventual consistency APIs, do you happen to call the callback for every edit, or do you only trigger periodically? Anything you do here is going to be depended upon very quickly. This is very fertile ground for Hyrum's law. Mixing up the behavior between build modes or randomizing it in some fashion might help, especially if you're not sure that the behavior that you happen to have or the implementation that you happen to have is what you want to commit to in the long term. And most importantly, just be as clear as you can be about when and how the callbacks will be called. This is a place where extreme precision is warranted. And we usually don't stress test these interfaces nearly as much as they deserve to be. If you don't plan ahead, you're going to be supporting whatever you first release, even if it turns out to be inefficient. There's polymorphism is another pretty straightforward way that we are introduced to extension. I would say generally lightly avoid it, right? It's certainly not the fashion for C++ in general anymore. But if it is the best answer, then please still spend 10 times more time on API design than you would otherwise. If you're designing an interface to be inherited from, you really, really need to put in more time and energy. A pimple approach may help, but it also has its own costs and subtleties. Any decisions that you make here are going to be very expensive to change after the fact, especially if your code lives in multiple repositories or is an open source project, or if you have enough code to make it hard to refactor all of the derived classes in one step. Even if you wind up with only 3 derivatives, a test, a production version, and something else, I've seen firsthand how much people balk when API design problems are identified in such a hierarchy. I catch one of these in the wild every month or two, and every time people ask, could I hold off and do that later? I'm like, yeah, fine. Also remember, your abstract classes and those interfaces are semantically kind of like concepts. They're both a set of requirements for things to implement and a set of functionality to be used by other code. Whenever you have that pattern, it's hard to change things. Inheritance, virtual functions have ABI implications. So if anyone in your code base is ever relying on precompiled versions of things, then changing the name or order or number of methods in such an interface is an ABI break. For things like plugin interfaces, this can become a dominant concern. You need to plan ahead a lot. Otherwise, the major normal form of extension in C++ is via templates and or ADL. You have a type that you want to work with our system, that's how you do it. Again, mostly just document things, take it slowly, carefully, document the intent more than the implementation. And remember that any protocol for when or how things are going to be called is just as much of a Hyrum's law trap as it would be in the case of callbacks. We've seen changes to these things. Stood accumulate changed in C++ 20, I think, moving from calling copy assignment to calling move assignment for the accumulator. So for stood accumulate on int or double, this doesn't matter at all. But if you were, for some reason, rinsing a vector of strings through stood accumulate, the question is, are we allowed to move assign that accumulation, or do we have to copy assign that accumulation? And that makes actually a big difference in the algorithmic running time of that change. Technically, stood accumulate was specified in the earlier days as very clearly calling copy assignment because there wasn't a move assignment for it to be calling. In the end, we decided that it is okay to make that behavioral change. And I think that the reason that it was the right choice is because it's a matter of intent. The intent is accumulate these elements with the implication of efficiency. And that's a sensible change to make. If the intent was instead, do exactly these operations, calling operator plus on a non-R value accumulator, that's a meaningfully different algorithm, right? And I think that this is an interesting descriptor, specifically because we came to the right conclusions, But I think that the reasoning behind it was mostly based on, I could argue that there wasn't any code out there, or was very little code out there that was potentially break under this type of change. And I think that the better argument was actually that this more faithfully matches the intent of the algorithm as specified. We also saw weird implications of all of this with abseils command line flags. Right? There were a couple instances of these sorts of Hyrum's law dependencies between callbacks and the order of flag parsing. Remember what I said about eventual consistency APIs? That one hit us here. If you implement command line processing by calling parse flag on every flag argument, a clever user can build a stateful flag type that tracks how many times it has been called. You could use that to build repeated flags or machinery to differentiate between this value was actually specified on the command line versus this is the default and nobody specified it. Neither of those designs is something that we specifically set out to support. In fact, we're trying not to. So it's mildly unpleasant, but because neither of those is the functionality that we intended, and we certainly didn't want to endorse it. But that's what happens when you build extension mechanisms like this. And we find gotchas hiding in even this very simple protocol every 6 months or so. It's a surprisingly subtle thing to get well specified without giving out extra implied functionality that you're going to have to support indefinitely. So in conclusion, let's summarize. The most important part of all of this is you want to focus your configuration based on outcomes and intent. Right? If there isn't a semantic meaning to the configuration options that you're sharing, then there's probably a better design for it. Customization is going to fight optimization and maintenance. If you can get away without letting people customize, without letting them configure, if you maintain more levels of that control, then over the long term, when it becomes useful, you can use those levers. Extension interfaces are very, very hard to get right and extremely hard to change after the fact. And of course, the popcorn button is a trap. And we'll take it to questions.
Thank you. Thank you, Titus. So I think that, like, for me personally, step-by-step migration with explicit intent approach is probably one of my favorites because it gives you kind of a way to make an experiment with some A/B tests and roll back easily. But let's try to answer one question quickly before we move on to the discussion where we can, talk more. So the question is, do you agree that the lesser options you provide for a user to configure, the better? Because the combinations often grow exponentially, and also you can predict the outcome of the usages more easily.
Yeah, for sure. I think that's the central tension that I've mentioned early in the talk. Users want these things, and it's sensible for them to want them. I'm not saying that they don't have a use case or a need for it, but the more of those that you say yes to, the harder it is for you to make changes or optimizations in the future, right? And so you're, in some respects, trying to balance one user has a use case today with some number of users have some number of use cases in the future, and those there's a lot of unknowns in that. It's very hard. So exercise great care.
Yeah, thank you. Okay, great. So thank you very much for the talk. And I really think that the people will go now to the discussion. Pavel Filonov will help driving it. So thank you for the talk again, and goodbye. And yeah, join the discussion. I guess it will be great. Yeah, thank you. Bye.